Okay, thank you for joining us at the second series of contributed talks. This is the session for applications of Maple, and we also have a few sessions that will be covering Maple in education. We have a nice lineup of talks for you to hear, and each speaker will have about 15 minutes to present and take questions at the end of their talk. If you have any questions you want to ask the speakers, you can use the Zoom chat to write it out, and we'll read it out. And also there will be an opportunity if you wanted to ask your question in person at that time. For the sessions that we have today, if you can kindly mute your audio if you're not speaking, and the sessions will be recorded so that you will be able to have a replay of those a few days after the event finishes. So first up, we have Matthew Calder. He's an employee with MapleSoft, and he'll be covering a Maple baseball scorekeeping application to generate defenses, optimize lineups, keep score, generate score sheets, and compute and display statistics. Matt, I think you have your screen up right now. Do you want to take it away?
Sure, thanks, Alex. So I'm going to demo and talk about a application I wrote in Maple to do scorekeeping. So the target is like slow pitch, so the variation of slow pitch of hardball, or of baseball rather, particularly for the organization. So that means generating lineups, generating defenses, and scorekeeping. Particularly, I'm going to do three pitch. That's a variant of slow pitch where the pitchers are pitching to their own teammates, so they also hit in the lineup, so they have to have pitching changes. So some background here. Common thing is players show up late, or they don't show up at all. They cancel late, or they arrive unannounced, or they have to leave mid-game. So there's some difficulties with generating the lineups and the defenses on the fly. As far as scorekeeping with pen and paper goes, it's also problematic. So that's why I've written this. The application can take in data with CSV files, so that's like the roster or the lineup, defensive scores. You can also export things. If you generate a lineup, you can also export it to a spreadsheet. You can also export statistics and other things. For defense, biggest challenge is if you have multiple extra players. You're trying to find where they play, give everyone equal playing time, as well as not have that at the expense of the quality of the defense. So you want to optimize the quality of defense given certain constraints. And one of those constraints is often number of girls. So slow pitch teams will typically have a minimum of girls that need to play. So if there's three girl minimum, you have to have 3 girls on the field at all times. As for lineups, the application can simulate them, give you an expected number of runs. You can also optimize it, try to find the best lineup given the players that you have there in a given game. Common scenarios like automatic outs, substitutions, players leaving mid-game, they can be handled. So for an automatic out, let's say the minimum is 3 girls, and you only have 2 girls, well, you can still play, but you have to have an automatic out, so that's handled. For the scorekeeping itself, the paper score sheet would be handed around between multiple scorekeepers, sometimes mid at bat, and it's very prone to like errors, like contradictions, missing information. So that's one thing I wanted to address with this application. So it does it much more quickly and much more accurately. So when you're scorekeeping, important information is at the ready. Things like the inning, the number of outs, who's coming up in the lineup. You take advantage of automation. So if, let's say you have runners on base and hitter hits a single, all the runners are advanced 1 base, and if they take an extra base, you can adjust as necessary. Things like the out number and the number of RBIs, they're automatically tallied. There's also macros for like common situations like a fielder's choice or a double play. There's also warnings and alerts. So let's say you haven't set the pitcher, it'll tell you haven't set the pitcher. You set the number of RBIs higher than the number of runs scored, it'll give an error. For the alerts, it'll tell you if like the pitcher's on deck, because if they're pitching, they have to come back in and do a pitching change so they can hit. It'll tell you something like, let's say the hitter hits against a better against a certain pitcher, well, I'll tell you that. So if you want to make a pitching change to take advantage of the matchups, it'll do that. Also in slow pitch, there's typically a mercy limit for an inning, like 7 runs. So a common thing you'll do is you'll yell it to the other team, 7's on 2, so that they're aware of that. So the alert will tell you if and where the mercy run is located. So you can also generate traditional score sheets, which can be exported. And this is math, this is Maple, this is baseball. Of course, there's statistics. We can do that, and I'll show that in the demo to follow. I'll first mention some future considerations. So this is geared towards 3-pitch and slow pitch, but there's some variations like hardball that I want to take into account. I don't record balls and strikes or stolen bases because they're not relevant, but in hardball they are. We can do more with statistics, more charts. That'd be useful. So there's running data and there's spray chart information that you can record, but they're not used. So I like to take that into consideration for the lineup optimization. So for example, the runner speed that factors in. If they hit into a lot of double plays or fielder's choices, that matters. If the runner goes first to third a lot, that matters. So that those things would be useful for the lineup optimization. And there's also the question of where is this going to go? Is it going to go in Maple Learn? Is it going to go in Maple Calculator, the application center, the Maple Cloud? So if Learn in the calculator, there's the issue of data. So importing data, exporting data, as well as saving data. So that may not work. So Maple Cloud or the Maple Application Center might be where this eventually goes. Okay, so without further ado, I'm going to switch spreadsheet or worksheets here. So there's options. So I'm going to mention that I've set the mercy limit to 7 for each individual inning, and there's many things you can change. I've loaded most things, so the data is already loaded. The game, so I've loaded the first game, I think. So make sure. So it's loaded. So what I'll do first is show you the score sheet of a completed game. Takes about 5 seconds to do all the internal things. So there's a bunch of things. So here, this is where you would set the opponent runs. So there's combo boxes. So you can set that. And of course, the arithmetic's all done by Maple and displayed in the scorekeeper. There's the details like the when and where and the who. You can also have the box score. So here shows all the inning runs and the totals. And you can see the score sheet here generated with all the nitty-gritty details, as well as the statistics for each hitter at the end of the game. And move on to the stats. I do believe it's already loaded. So the overall stats are already loaded. So I'll show that. So you have a chart with all different statistics. The leaders are hidden, or highlighted rather. You can see the matchups. Each individual hitter against each individual pitcher. You can see how some hitters will hit much better against certain pitchers. And something think about baseball. The closer you look at statistics, the more it doesn't make sense. The more you scratch your head. And there's also a bunch of charts you can do. So some hitters are hit better on certain diamonds or certain months against certain opponents. That's to be expected. Sometimes it's varies widely for a particular hitter on a given day or the start time of the day. So one thing I'll mention that I want to do in the future. So right now you can only select one hitter or all hitters, but I like to do multi-select. So I've got that working in the back end as well as the charts. I just got to update it in the GUI. So on to scorekeeping. So first of all, I need to load the game. So I don't think I have it there already now. So I have to import it. So I import it from a CSV file. It's going to load all the games, including the one for the exhibition game. So I'm going to do, so I created an exhibition game for right now. So this is what we're going to do for the demo. So that's, let's load that again to be sure, load a game. The lineup, I'm going to load a lineup. on the CSV file demo lineup. As you can see, you can manipulate it in the application if you want. You can simulate it to see the number of runs scored. You can optimize it. You can also do it by matchup. So if hitters hitting against their preferred pitchers, and you can also group them, the pitchers, so that you're not making pitching change after every at bat. So when I loaded the lineup, I'll mention it also loads the bullpen, so you can do it in one go. So the defense, this is based on the lineup, so it's filtered by the hitters in the lineup. I'm gonna disable this here. So if you want to find, so the scores I mentioned, so 0, you don't play, 1 to 5 on your ability. So I generate that. I'll just generate a table. All right, so you can change the scores in game if you want. So the numbers are 0 to 5. And here's a table that you could print off and display for the players to know where they're playing. One thing you'll notice is that the lowest score is 2.4. So the average score for that particular inning is 2.4. We'll see if we can do better. So if I say use the scores, I'm going to set the minimum average score to 4.3. There's a reason for that. Click generate. 5 to 10 seconds later, it will tell me that it's found a solution. So refresh. And there's the requisite mistake that's not working. Let me clear that and refresh. Oh, that's what's complaining. Whatever. So generate again. If that works. I'm not sure why it's not showing the actual scores. But in terms of time, I'm just going to continue. But it's time at the end. I'll reload the thing and do it that way. Oh, here it is. So things that magically go wrong in a demo. This is what it was. You can see here. Sorry, that's a statistics. What I'm thinking. Whatever. Yeah. So I'll do offense. So I'm going to score keep a 1 inning game. All right, so I click new play. Okay, so the warning says I need to add a pitcher. So let's say, so the alert tells me Greg is the preferred pitcher. So let's have him pitch first. Let's say he hits a single. We'll automatically put it first base. To complete the play, that's the next one. Let's say the next hitter, which would be John. John hits a single. It'll automatically move Ken to second base and put John at first base. Complete. Let's say Kyle hits a double. So Ken's automatically going to score. John's at third base, but let's say he took an extra base and he scored, so you can do that. I also notice that the RBIs are automatically tallied. And if I were to set this to 3, it'll complain that that's not possible. Right, so I'm going to put that back to 2 and then move on.
We're just coming out towards the end of the times, Matt. Was there? I like the fact that you can load things by CSV as well as enter them straight on the screen. It gives you a lot of flexible options. There was a question that came in on the chat. If you're okay to take that.
Sure. I got to find the window first.
That's okay. I'll just read it out for you. Sure. So I think there was this looked like there was an early draft of this in one of the Maple Cloud. Was that your handiwork?
Yes, it was. So that was the lineup simulator and optimizer. So the idea of this is to take it to the next level.
Looks very slick as an interface. Did you find that you needed to refine the procedures a lot to optimize the Maple runtime and the storage constraints?
Oh, absolutely. So I was doing that a lot. So I always make sure I time things and check the efficiency. So yeah, there was a lot of things that would, if you didn't do that, it would be very slow.
Quick question for Matt. So you use a lot of components for the interface. The score sheet, can you talk about how that was generated?
So there's a lot going on there. So with the images for the individual entries, so there's the issue of text plots and line plots and point plots. If you resize them, they overlap, right? So what I did was I create images for each individual component. So there's an image for the blue circle for NRBI, for example, and then convert that to an image tools image. So that's an array, 500 by 500 by 3. And then I save them to a repository. So when you go to generate the worksheet or the score sheet, it'll determine what it needs and look for those individual images in the repository. And if not, it'll create them and then add them to the repository. And it brings them together to one big array tools or image tools image. And it'll display that in a component, an image component. And then the rest of it is generated with like, document tools, layout. It's a programmatic creation of the embedded components.
There was one follow-up question for the version, I think, on the Maple Cloud. Do you use multitasking for the lineup simulator?
There's the option for threads and grid. Right now, I don't use it too much. I just use the regular mode. But there's those two options, so it does help a lot. So if you really want to go above and beyond, do like 1,000 permutations, then you can use grid.
That's really cool. Well, thank you, Matthew, for showing us your application. Very interactive. We're going to be moving on to the next presenter now.
Thank you, Alex.
So we have Tomás Recio. He's joining us from Spain. His team were also presenting in one of the earlier sessions, and he's going to be describing through Maple GeoGebra's discoveries, new features, proof certificates, and complexity estimation. So if you can get ready there, please, Tomás, and you can see your screen now.
Okay.
Yes, that's great.
Well, so in some sense, this is a talk, a presentation that is not that different from the previous one. In some sense, our game here is not baseball, but elementary geometry, Euclidean geometry at school. In some sense, also, our player is GeoGebra Discovery. That is an automata, that's a robot that discovers geometry theorems. And what we want to do is to keep a record of some kind of scores about the theorems that he proves, that this robot proves. So this is our idea, and it's not quite original. The idea of ranking geometry theorems goes back into 1988, and it is a question that has been behind artificial intelligence for the last, I will say, 40 years. And now it's becoming more and more, because artificial intelligence is performing better. It is more interesting now to, in some sense, to score, to identify, to grade, to evaluate the results of using automatic reasoning programs on a topic like, for instance, elementary geometry. So what we do is to present here, that's my talk here, is to present a new command called the showproof command that allows you to grade, to score planar geometry theorems. GeoGebra Discovery, as I said before, is a kind of automata that if you can ask, please tell me theorems about this figure, he gives you a lot of theorems. Or you ask the machine, please tell me if what is the relation between these two objects, states a theorem. You can also, of course, state a theorem and ask the machine, is this true or false? So it's a kind of automata, but I am looking more to the performance of this GeoGebra Discovery, not to verify my theorems, but to discover new theorems. And I want, in some sense, to score these theorems. Why are we interested in finding this complexity measure of the discovered theorems? First of all, because if we have a score, we can, in some sense, improve the performance of GeoGebra, because we understand it will be not the same to perform badly for trivial theorems than to perform badly for theorems of the mathematical Olympiads. Or maybe we want also to ask the machine, please tell me theorems about this figure, and we want the machine to give us theorems of the certain level, not trivial theorems. Also, we want to use, and this is also is getting very interesting, to adapt GeoGebra reasoning tool to students with different levels, with different educational needs. Like, for instance, students with difficulties in mathematics or students with mathematical Olympiads. Also, we want to do some collaboration with ChatGPT. We want to see if ChatGPT and GeoGebra Discovery complement each other for theorems of this level of difficulty, or maybe ChatGPT doesn't work well for theorems of this other level of complexity, while our robot works well. So we want to measure this in some sense. So what is the idea? The idea is to do it using algebraic geometry. And the idea is quite elementary in some sense, quite elementary. We say that the statement is difficult if the thesis is difficult to express as a combination of the hypotheses. In some sense, if the length of the proof is quite long, as the longer the length of the proof, the more difficult should be this theorem. So sometimes the hypotheses are very complicated, but the thesis is one of the hypotheses, so it will be trivial. So it is the comparison between the expression of the thesis in terms of the expression of the hypothesis. And this is our proposal for measuring, in some sense, geometry theorems. This is the formal algebraic input. We have some hypotheses, which are algebraic equations, multivariate polynomial equations. We have a thesis that is also a multivariate polynomial equation, and we want to prove that this collection of hypotheses imply the thesis. And then maybe we can do it. It is better for some algebraic geometry reasons that I am not going to detail here. Sometimes it's better to go in proof by contradiction. That is, if I take the hypothesis and the negation of the thesis, so t times theta minus 1 means that the thesis is negated. So I want to show that this is empty, that there is not a point in which the thesis is false and the hypotheses are true. So I want to see what is how complicated are the polynomials f1, fr plus 1, that in some sense are my proof, are the certificate that this theorem is true. And so the degree of these polynomials, the maximum degree of these polynomials, will be for me the rank, the score of this statement. For instance, let me take here Pythagoras theorem. So I take here a triangle ABC. So I assume that the right angle is at A. So this is the equation equal to 0. That means that AB is perpendicular to AC. And the thesis is that the AB is equal to AC. AB squared plus AC squared is equal to CB squared. This is the thesis. And really, if I expand the thesis, I see that the thesis is exactly equal to the hypothesis. It's only 2 times. So Pythagoras theorem is trivial in the sense that the thesis is only a constant times the hypothesis. So I will grade this statement as degree 0, grade 0 or complexity 0, because the degree of 2 is, of course, is a constant, is degree 0. So here you have another example. I have 2 points, A and B, and I take the perpendicular bisector, and I want to prove, this statement is quite simple, that every point in the perpendicular bisector has equal distance to the 2 points A and B. So I want to show this, and my machine tells me that this has complexity of degree 2. So it's quite elementary, and this is what I do with Maple. I take, to show you the result, I take the thesis, I take the collection of the hypotheses, and I show that the thesis belongs to the ideal of the hypothesis, so it is true. And so I want to express the thesis as a collection of my hypothesis. I compute the Gardner basis, and I express every term of the Gardner basis in terms of the given hypothesis, and I see that only require some constants. And now my thesis is a collection of is a combination of the Gerner basis multiplied by polynomial of degree 1. So degree 1 here, constant here, the total degree is 1. So this is the verification. So this is a little bit the idea which is behind this. I have no much time. Let me go a little bit faster. So for instance, this is Ptolemy's theorem. This is the theorem that you have is a quadrilateral that can be inscribed in a circle. Then f times g plus h times I is equal to the product of the diagonal j times k. So I ask the machine, please tell me, is there any relation between the product, the sum of the product of the opposite sides and the product of the diagonals? And the machine tells me, yes, they are equal, and this is the proof, and the complexity is 7. So you see, Pythagoras was complexity 0, this bisector was complexity 2, this Ptolemy's theorem is complexity 7. Oh, here you have another example of our, we make this octagon here, and now we construct these two squares, and I ask the machine, please tell me all the theorems that you can imagine over this figure. And the imagine gives me 2,000 theorems in a few seconds, 2,504 theorems in about 8 minutes. So some of these theorems, like n belongs to the circle IEM, they are interesting theorems. Some of the theorems are trivial, declaring, for instance, let me try to find one of these first. Here, I belongs to AB. Well, this is trivial. I is A. So this is absolutely trivial. So this is one of the things we want to do. We want to have our automated geometer answering, giving us only interesting theorems, not trivial ones. Okay, so let me finish with a little bit with some questions for Maple programmers. Is there any better algorithm than this one? The one I did with computing the Gerner basis and then computing the expression of the thesis in terms of the Gerner basis, and then every element of the Gerner basis in terms of the given generators? Do we need to compute the full G basis for deciding if some ideal is 1, the proof by contradiction? How can I guarantee that I am computing the lowest degree? So I have many. For instance, over the reals, I want to have also statements over the reals, but people that know a little bit about real algebraic geometry know that over the reals, the fact that some ideal is empty is not because 1 belongs to the ideal, it's because 1 belongs to the real radical of the hypothesis and the negation of the test. So the question is in Maple, can I in Maple compute, as I did 1 in the Gerner basis, compute 1 in the real radical? Can I compute in Maple the real radical? This will be very good to import this into GeoGebra Discovery. Or for instance, this is the question I have over here. Or for instance, if I have not only a figure with equations, but a figure with inequalities, I would like to express my thesis equal to 0 over the hypothesis if and only if, and here we have what we call the positive Stellensatz, but it is not clear. I never seen that implemented in a program like Maple. So we are wondering about this future work, and this is what we're trying to do. We're trying to compare the difficulty for humans and for artificial intelligent bots. We want to see if the people have the same feeling as I have, that the Ptolemy's theorem is more complicated than the theorem of the bisector median or something like that. Or I would like to, there are many computer algebra theoretical problems that are related to our approach and that nobody seems to know right now to solve it. And this is, I think, we have to do a large number of tests, and this is initial work. So thank you so much.
Thank you, Tomás, for taking that through. We have one question that's come through in the chat I will attempt to read it out, is t times z minus 1 the same as t times, in bracket, z minus 1? It seems yes.
No, the answer is no. So when I am trying to declare that t is not 0. So when I say t is not 0, I write the equality t times zeta equal to 1. No, this equality has never solutions with t equal to 0. If t is equal to 0, 0 times zeta cannot be 1. Okay,
That's
so
fair.
this is what we call, this is not my idea, this is called Rabinovich trick. And it is quite common in algebraic geometry. So this is the trick we are using. Okay.
Thank you.
What
yes.
is the complexity level of the Euler line and Heron's formula? Very good. So see, this is what happened with the machine. We become all curious. I am asking the machine, is there any theorem about the sum of the sides of a triangle and the product of the heights? Well, maybe it is. Maybe there is. Is there any, for instance, Pythagoras in my version, is there any theorem that says the square of a side is equal to the product of the other two? What is the relation between the square of one side and the product of the other two? When this happens, tell me what kind of triangles. Okay, so Euler line is more complex. It's about, I don't remember, but maybe complexity 5 or something like that. And Heron's formula, I don't know if I tried. For Heron's formula, we have a little bit of problem because Heron's formula has a square root. And for people like me in algebraic geometry, square roots are forbidden because a square is not a polynomial. Square root is not a polynomial. So really, Heron's formula should be with the square. But I think my impression will be complexity 5, 6, something like that. And we have measured with problems from the mathematical Olympiads, and we have achieved even a complexity 34. So it is very interesting. It's work in progress, but very interesting. And we use Maple because, of course, the GeoGebra Discovery works on a smartphone, is very small, and it's very difficult to check the equations that finds. So we have developed a way to export GeoGebra Discovery to Maple. So we export it to Maple and we analyze and try to understand using Maple what is going inside. Okay.
Thank you, Thomas. Just in the interest of time, we will move on to the next presenter. But I appreciate your time, and if you want to reply in the chat to some of the questions, that would be awesome.
Thank you. Thank you.
Our next presenter is Bahia Lakhal. He'll be joining us from Algeria University, and he will be covering the solutions of Lane-Emden equation. Bahia, if you're able to join us, could you share your screen and take yourself off mute?
Okay, I present myself. I am Bahia Lakhal. I am a physicist teaching and doing research at a university in Algeria. So thank you for giving me the opportunity to present my work in front of the community of Maple software users. In fact, I started using Maple in 2016 for research purposes. Now I use it in teaching at graduate and undergraduate levels. Today, my talk is about the solutions of Lane-Emden equations as a Maple application. So the Lane-Emden equation is a nonlinear second-order equation. It is named after astrophysicists Jonathan Homer Lane and Robert Emden. It was initially used to describe the gravitational potential of a spherically symmetric polytropic fluid, but now it is applied in different branches of physics. Polytropes are very useful in astrophysics as they provide simple solutions for the internal structure of a star. Now, to get the Lane-Emden equation, we have to write two equations: the equation of continuity and the equation of hydrostatic equilibrium. M is the mass of the polytrope, rho is its density, P is the pressure. G is the Newtonian gravitational constant. For a polytrope, in fact, a polytrope refers to a solution of Lane-Emden equation in which the pressure depends upon the density rho with this relation. P is equal K gamma to rho to gamma. Gamma is the adiabatic index related to the polytropic index via this relation. K is a positive constant. Now, to get the Lane-Emden equation, we have to eliminate the mass between the two equations, the equation of continuity and the equation of hydrostatic equilibrium. We get this equation. It will be useful to write the equation in dimensionless form. So if rho c is the central density of the polytropic star, we can write the density as a function of theta. Theta is a dimensionless function. The pressure also is written in respect to theta. We get this equation. Now this equation is dimensionless with respect to theta, but we have to rescale the radial variable r by the constant alpha, and we get the Lane-Emden equation in dimensionless form. We see that this is a non-linear second order differential equation, which depends on the polytropic index n. So now we are ready to solve this equation using Maple software. So we will get solution to every value of n. As I said, the solutions of the Lane-Emden equation are known as polytropes. The index n will determine the order of that solution. Now, because this differential equation is second order, we need two boundary conditions. The boundary conditions are theta at xi equals 0 equal 1, derivative of theta with respect to xi at xi equals 0 is 0, theta at xi1 equal 0. The first condition ensures that the density at the center of the polytrope is equal to the central density rho c. The second condition ensures that the solution is regular. The third boundary condition is written in order to find the radius, to estimate the radius of this polytrope. Okay. So how to find how to estimate the radius of the star? We write this theta at xi1 equals 0. We find xi1. To find the radius, we have to use this constant alpha. So r, the radius, is alpha times xi1. Okay. So now, using this Maple software, we get the solutions of the Lane-Emden equations for different values of n. We have two kinds of solutions: analytic solutions and numeric solutions. The analytic solutions are found only for three values of n: for n equals 0, n equal 1, and n equal 5. So for n equals 0, we get the following solution. We see that the density of the solution is, as a function of radius, is constant. So this polytrope will explain well for example, some rocky planets. The radius is found if xi1 is equal to square root of 6 by the boundary condition theta 0, xc1 equal 0. So the radius of such a polytope is equal to this value. For n equal 1, we get the following analytic solution. This solution describes some kind of dwarfs. The radius of the polytope is given here. Now, for n equal 5, there exists an analytical solution, theta index 5. This solution is finite in mass, but it's infinite in radius. So therefore, this kind of solution doesn't represent a physical solution. I have to bring your attention here. I tried to, using Maple 2018 software, I couldn't find the analytic solution. The program was running more than 1 hour without having the solution by using. So what I did, what I do, I used the dissolve option series. I got this series. No, I know that the solution for n equal 5 is this solution. So what I did, I make series of this solution, and comparing equation 21 to 23, we see that we have the same equations. So this is the analytical solution. There exists 2 other well-known solutions, the Srivastava solution and this another solution, which are both singular at xc equal 0. So in fact, this solution belongs to a larger class of solutions valid for n greater than 3. The solutions with the polytropic indices greater than 5 have infinite radius and also infinite mass. So the solutions with n greater than 5 have no physical meaning. So it's not interesting to study them. Now, there exists an interesting case when the polytropic index is in the range between 0 and 5, which has numerical solutions. So with the help of Maple software, we can find the solution using the package tools, using the command dissolve with either the option series or the options numeric. For example, I give here in this talk the solutions in series for n equal 2, for n equal 3, for n equal 4. For example, for n equal 3, it is a solution called in astrophysics the Eddington approximation. It corresponds to fully radiative star, which is a useful approximation for the sun. So using the package plots with the command audio plots, I displayed here the variation of theta as a function of xc for the polytropic indices n equals 0, 1, 2, 3, 4, 5, and 6. Now, for a given polytropic index n equal 3, which is, as I said, in the case of Eddington approximation, for example, for a white dwarf series B, I plot here the density, rho, and the pressure as a function of the dimensionless radial variable xc. We can find, for example, the radius of the white dwarf from here, for example, from the plot here, which corresponds to the black plot here. We see using, for example, the cursor given in plot, we can find the radius of the star.
Now, Bahia, we're just coming close to the end of the time. Do you have a final thought to leave us with?
So conclusion, in this presentation, using the powerful software Maple 2018, we have given analytic solutions of the Lane-Emden equation for the polytropic indices n equals 0, 1, and 5, and good approximate solutions in form of series expansion for n equal 2, 3, and 4, with which we have plotted the solutions and the behavior of density and pressure for a particular value of n equal 3. The analytic solution for n equal 5 couldn't be obtained by Maple 2018 using the command desolve. The reason I think maybe is that we have two other different analytic solutions. So for this reason, the program was looking for solution, but without giving it. So thank you for your attention.
Thank you, Bahia. That's really amazing to see the differences with the different n values and comparing it to that white dwarf example too, to see a real world case too. If you have a question for Bahia, if you could type it into the chat, and I will just ask a quick question to you. Was there other solutions you had tried to solve the differential equations outside of Maple? Had there been previous studies that you had taken the differential equations from, or was this something that you worked in with your team?
No, just this is work done in the literature. So in general, I give it for students in undergraduate just as application for in Maple.
Awesome. Is there anyone else with a question? If you'd like to unmute or type it into the chat. I think you have done a thorough job explaining it. Everyone is happy. Thank you, Bahia, very much for your time. If you'd like to just unshare the screen, we'll move on to our next presenter. Thank you again. Okay, we'll be moving on. We are going slightly out of order. There's one of the speakers has not joined our session yet, so we're just continuing with the sequence right now. With next speaker is Samir Hamdi. He's from the University of Toronto in Canada. He'll be covering the Maple simulation for traveling wave solutions for FitzHugh-Nagumo model equations for nerve conduction in an excitable reaction diffusion system. Samir has been generous enough to speak at several Maple conferences before, so it's always a pleasure to hear from him and to catch up with some of the latest developments in his research and his studies. Samir, if you're able to share your screen.
So as Alex mentioned, so this continuation of the previous work on the simulation of the propagation of pulses in neurons. And the model is FitzHugh-Nagumo model, very famous, important model. And we look for the propagation in excitable media as well with the diffusion. So I will present some previous results from previous work, but as well I will mention the new developments in this research work. So traveling of pulses in reaction diffusion system, as you can see in the outline of the presentation here, is based on studying the coupled set of a system of FitzHugh-Nagumo model. This is a nonlinear model, and it's for the propagation of pulses when there is action potential, and as well we look for the recovery or the inhibitor as a result of that. So it is very important because it has importance in biology as well in neuroscience, but as well in deep neural networks. And when we have an analytical solution, so it becomes handy because we can check or interpret results easily. So the derivation of the solitary waves are obtained using Maple. So it's based on solving a fourth order boundary value problem. And to solve that, we need to solve a quartic polynomial. As well, we need an identity that developed recently, and it makes the solution easier with Maple. And once we have the solution handy, so we try the simulations using the method of lines, and by using the solution as incipient wave, and we let it propagate in the axon in the fiber neuron, and we look to the interaction of the solitary waves. So basically, we have a system of solution of equations that are a system of partial differential equations. Let me here choose the pointer. So in this system, we have the dependent variable u is the activator, and depends of time, so it's partially derivative with time. And we look to the propagation in the neuron, in the axon of the neuron, and we have a nonlinear term here. And for the inhibitor or the recovery variable is v, is also covered by partial differential equation. So basically, to give you some ideas about studying this propagation of pulses in neurons. So there is fundamental work carried by Hodgkin and Huxley in 1952, and they based their experimental study using giant squid, because this giant squid, it has a huge, big axon. Compared to the humans, we have like the axon for the neurons in the brain is just diameter is a fraction of a millimeter. So this is a giant squid axon, and they studied and they discovered very important that there is an ionic mechanism that's really underlying the initiation and propagation of the action potential in the neuron. And they also provided a model, and that model was very important and was really the beginning of research in this area. And they get the Nobel Prize in medicine and physiology in 1963 for their work. So basically, this is the neuron that you can find in any textbook, or this is from Wikipedia. So we are looking for the propagation of pulses in the axon of the neuron. So a single pulse in the axon of the neuron. And the propagation of the pulse is, there's an action potential nerve impulse that travels down on the axon. And it's because of the change in electric polarity across the membrane, as you can see in this illustration from Wikipedia, and in response to a signal from the synapse coming from another neuron. So, and there is gates for ion channels for sodium and potassium, and they open and close, and that makes the membrane, there is potential, and when it reaches the threshold, so there is the propagation of the pulse. So back to the equations here. So we are not using the Hodgkin-Huxley model because it's only unidirectional model, but rather we use a very well-known model, which is generalization of the Hodgkin-Huxley model, which is the FitzHugh-Nagumo model. So it's a set of two partial differential equations, as you can see here, and it allows for the propagation of the pulse in two directions, so bidirectional. And also it includes the diffusion term that you can see here. And there is a nonlinearity f of u that really gives you the shape of the pulse, and it's difficult to solve because of this nonlinear term. So to deal with the nonlinear term for the solution, for looking for a solution for these models, so in many authors tried many forms of the nonlinearity. So for f of u, for example, one of the well-known nonlinearity form is to use cubic-like nonlinearity. So f of u would be u times 1 minus u times u minus a, and a is a constant, a parameter that really gives you an idea about the shape of the nonlinearity. So still, when you use this cubic nonlinearity, is still difficult to solve analytically. So although we can solve it numerically, so there is another way is to use the piecewise linear form of the nonlinear term f of u. So linearize it using the Heaviside step function, as you can see here. So using that, then we're able to write the equation, cast the equation in using the Heaviside function. Now, when we look for pulse solutions, so it becomes a boundary value problem, because the pulse, it has kind of a bell-shaped, it's localized wave. So we will use the very common in the case of propagation of waves to use a moving coordinate. So the moving coordinate will be z equal x minus ct, where c is the celerity or the speed of the wave. So using that moving coordinate, then we, instead of having the two independent variable x and t, so we will have the independent variable become z. And for that, so the partial differential equation, system of partial differential equation, becomes a system of two ODEs, as you can see here. So when we eliminate one of the variables, for example, if we take the activator UC, we eliminate it, and we base the solution on the inhibitor or the recovery variable, then what you can see here is a fourth order boundary ODE, and we have a linear form, and we can solve using Maple. However, to solve it, then we need to solve first the associated polynomial, fourth order polynomial. So we solve this quartic polynomial to find the roots alpha 1, alpha 2, alpha 3, and alpha 4, and solving that, and also using an identity that I will show you later. So it becomes possible with Maple to find the solution piecewise solitary wave for the activator U, the action potential U, as well for the recovery variable V of the propagation of the pulse in the axon of the neuron. So for the solution of the quartic, although there is a solution, but it's complicated using the radicals, I developed here a compact form of the solution using very important capability in Maple, which is the hypergeometric function of Gauss. So this solution is written in this form, and where G1 and G2 are simple hypergeometric functions of Gauss, and H1 and H2 as well are also hypergeometric functions of Gauss. So it's a compact solution this way. But also to be able to solve this system, I use this identity which is similar to the Vieta and the Newton formula for polynomial. So this formula identity is based on the derivative of the polynomial, of the fourth order polynomial, but evaluated at the roots of the polynomial. And this formula is similar to the Vieta or Newton formula. It's a new formula. Really, it's very important, like to find this important formula because the study of polynomial is very much studied and classical field, but to find new identities is really very important. And we have these identities that are for the case of distinct roots of a polynomial. So these are the important formula that involves the derivative of the polynomial evaluated at roots, like p prime x1, p prime x2, p prime x3, and p prime x4. And for the roots x1, x2, x3, x4, and its identity that depends on the coefficient of the polynomial. So using these identities, then it's possible to find the coefficient of the piecewise solitary wave solution, as you can see on this left here. And if I go back to the slides, so these are the coefficients that you can see here. So it's possible using Maple and using the identity that I discovered to be able to express the solitary wave solution, as you can see here. So the shape, of course, is a solitary wave. So the shape is given here. So in the blue curve is the neural excitation of in the axon of the neuron that propagates along the distance is the distance along the axon, and the what you see the blue curve is the action potential, and the recovery variable, the inhibitor, is the curve in red. So this is a bigger picture of it. And this is obtained using Maple. So compared to the previous results that I presented in the previous conference, so we added these new results is that we're able using Maple to find a relationship plot, analytical plot that gives us the speed or celerity of the wave as a function of the parameter A. Remember, the parameter A, as you can see, is a parameter that gives us the shape of the nonlinearity of the in the model, and this is for different values of D. So in the additional material that I will submit to the Maple soft, will provide the explore plots using Maple, because you can use a slide, and it's very really handy, because you can see really the influence of the value of the parameters D on the solution of the graphs plots of the celerity as a function of the parameter A. So also the other new result is that you can see here at the right is the celerity as a function of the width of the solitary wave. So I can show you here in the graph, the width is from 0 to Z1 is the width of the solitary wave. So the solitary wave, so the speed or the celerity of the waves really depends on the width of the wave. So if you have narrow or wide wave, then it will affect the celerity of the wave. And of course, these are given for different values of D, and D is the coefficient of the diffusion, because this is the propagation of traveling solitary waves in diffusive media. So, and this is really important because we were able to find this relationship between the celerity and the width of the wave. Now, using these solutions in Maple, so we use MATLAB, or we can also use Maple, because Maple now it has numerical solution capabilities for partial differential equations using the method of lines. So we use the method of lines, and we put in the middle of the axon of the neuron the stimulation, a single pulse, the one that we obtained analytically, and we let it propagate, and you can see that it's bidirectional propagation of the signal from in opposite directions, and is really an illustration of the propagation in the neuron. Now, this is another plot like 3D. So what you see here in the pointed red spot is the stimulation of the action potential here, and the time axis is in this way. So when it propagates in time, you see that there is two solitary waves emanating or generated from the initial solitary wave that you see here. Now we have similar plot as well for the recovery variable, and so these are the results that we obtained. So as a conclusion, so we studied the traveling of wave pulses in the reaction diffusion model of the well-known couplet set of FitzHugh-Nagumo model. But in this case, we added diffusion. So unlike the previous studies, we added diffusion in this model, which is really, it has physical meaning, diffusion there in this medium. And we studied the solitary wave solution that we obtained using Maple, and based on a new discovered identity for polynomials. And we used method of line simulation of traveling wave solutions to perform stimulations, and we see the propagation of the pulses in the neurons. Now, one more important aspect of this identity, I will go back to the identities here. So these identities here are used in the case of a fourth order polynomial, but these identities are general, so they're for any polynomial. So using brute force, we can show that this relation holds using Maple for third order cubic polynomial, quartic, fourth order, quintic, sextic, up to 10th order, we can do it in Maple. But for higher order, there is mathematical proof, so we developed the mathematical proof that this identity holds for any degree of polynomial. As far as the derivatives are non-zero, and the roots should be distinct roots. So x1, x2 are distinct up to x4 in this case. So as a conclusion, so we also we reproduced most of the results in this paper, very important paper by Aito and Ohta, so the two Japanese researchers in 1992. So we're able to proved, and we were able to derive all of the results using Maple in this paper in 1992. So for those interested in our work on solid wave solutions, so I listed the publication here. And the code that we use is developed by Professor William Scheser, and the code is available from the books my co-author William Scheser in 2 or 3 of his books. So there is extensive information about the method of lines. We have also 2 entries in the Wikipedia as well as Scholarpedia about the method of lines. So I think
Thank you.
this is the link for a method of lines. Scholarpedia is article 9. So thank you for your attention. If you have questions, so thank you very much.
Thank you, Samir. We do have one question that's come through on the chat. What happens to the wave at the end of the axon? Does it reflect back? Is it especially important if the simulation is near the end of the axon?
So at the end of the axon, it will be transmitted with the synapse to the other neuron. But in this case, we did not impose boundary condition. So if you impose boundary condition, so that will affect the solution. So we can impose, for example, absorbing boundary condition. Like this is very common in water waves, for example, in the water flow, or we can impose a periodic boundary condition. So when it exceeds the domain, it will re-enter from the other side. But in this case, so you see like how it's complicated in the human brain. So this is one single neuron and how it's complicated to study. But thanks to this analytic solution, so we can now use a network of neurons, and this is why it's important for deep neural networks. So this kind of work. So
Well,
it has some.
I know that a lot of the studies have started with the squid because it is simpler. So moving over to the myelin models adds a whole level of complexity. So that building up on the human design is
Yes.
going to be a powerful research study. Thank you.
So this is how Hodgkin and Huxley they did the fundamental work, and they get the Nobel Prize for that kind of study. And,
next time it will be you, Samir, right?
Thank you very much.
Thank you very again for your time. I appreciate that. If you don't mind stop sharing, we'll just move to the next speaker, but appreciate your time.
Thank you.
There is also one more question in the chat. Perhaps, Samir, you could, while we go to the next person, just maybe respond to that one as well. We have had unfortunately, one of our speakers hasn't been unable to join us today, so we are moving to the next speaker, which will be the last in this session. We still should finish around the same usual time as planned. We next have Al Rusnak from Microchip USA. He's going to be sharing a study on the stochastic and predictive scheduling technique for mega projects, which is using Maple in a project management setting. So Al, if you're able to share your screen and come off mute, that'd be great.
A stochastic and predictive scheduling technique for mega projects. Welcome to all the Maple users all over the world. My name is Al Rusnak. I'm happy to be able to present at the Maple conference again. I am a program manager at the Microchip FPGA business unit. This business unit specializes in developing FPGAs. I specialize in scheduling of these very large programs. Also, I've been a MapleSoft ambassador for several years now. The discussion today, we'll first talk about what is an FPGA. Second, what were the objectives of the scheduling exercise? Third, the algorithm and the process control details, and then I'll summarize. Brief FPGA description. An FPGA is a field programmable gate array. It's an integrated circuit that can be programmed to perform a variety of tasks. FPGAs are some of the largest semiconductor dies. There are 2 types of IPs used in an FPGA, mixed signal and RTL. The mixed signal IPs, intellectual property, are the analog parts, and the RTL IPs are the digital parts. A single IP is usually broken into smaller blocks, and the blocks are what we scheduled for this exercise. The total number of milestones in the schedule for all of the blocks is very large, in this case around 5,000. What were the objectives of the exercise? One of the most important milestones in the semiconductor design process is the tape-out milestone. I needed a method to analyze a large matrix of milestones, but could not use the provided dates. I knew the dates were invalid. A stochastic method was needed to monitor the progress of the program and to detect statistically significant differences. Finally, a method was needed to predict a range of dates for the completion of the IPs that gated a tape-out milestone. The first step was to pick a subset of the 50 milestones per IP block. I recommend picking 4 to 6 milestones per IP that are the most important and evenly distributed over the life of the program. For this particular program, I picked 4. The graph shows the number of milestones remaining as a function of time. Initially, the number of milestones is approximately 100. The data points start to show a trend after several updates. In this case, the analysis started with approximately 10 data points as shown, and it's within the green circle here. Curve fit. Since I did not know what curve fit would be the best, I tried 16 curve fit options. 8 were polynomial, 6 were nonlinear, 1 was exponential, and the last was a power fit. The blue dots show the data. The black lines show all 16 curves from the curve fitting algorithms. The question was, which one should I use? To start the curve selection, it's logical to assume that all programs have a finite number of milestones at the beginning of the program, in this case, 96. Also for a normal program, the slope of the curve must be negative. This means that the number of remaining milestones should decrease as a function of time. The curves that meet this criteria are shown. So the curve selection continues. For a program to be complete, the number of milestones must be 0 at the end. The 2 curves that cross at the x-axis are shown. Rho squared was reviewed with the objective of using the curve with the largest rho squared value. Additionally, the blue diamond was the target date provided independently. This indicates the desired target date for the completion of the program. The final curve, after reviewing all the desired target date and rho squared, the final curve was selected, which is this one here. So the project had specific business goals. The goal was not just to predict a single completion date, but to define a business process that could determine confidence limits and be used for scheduled process control. The business goals required the data analysis of the milestone data. The randomness around the selected curve was determined. If we subtract the curve fit equation from the data points, the randomness around the curve was determined. The random data is shown in the chart. Then the mean and standard deviation of the random data was calculated. Finally, a normal distribution function using the mean and standard deviation was generated. Now that we have a defined curve and a statistical information, the process control limits can be generated. Recall that the black line is a curve that has been chosen. A set of curves representing +1, 2, and 3 sigma are shown in red. Also, a set of curves representing -1, 2, and 3 sigma are shown in green. The diamonds represent possible target dates, i.e. dates provided by management. The blue diamond represents a target that is within the process control limits, meaning that the estimated date is very close to the desired target date. The green diamond represents a target that is later than the process control limits, meaning that the estimated date is earlier than the target date. The red diamond represents a target that is earlier than the process control limits, meaning that the estimated date is later than the target date, which is a potential missed schedule. Now let's describe the process control. To stay under control, the point should stay within the ±2 sigma curves. However, when we add it to a new point from the periodic updates that goes beyond the ±2 sigma curve, an action plan should be developed. This plan is generated before it's actually needed. The action plan can be defined to either resolve the issues that have been identified or to redefine the curve and obtain new estimated dates. Now, when a point goes beyond the plus or minus 3 curve, sigma curve, the action plan should be implemented. The solid red line is used to highlight how serious a schedule deviation is. If it's too steep, it becomes unrealistic to believe that the target can be met without some major adjustments. This line is very effective in illustrating the seriousness of the schedule situation to management. The process control limits are great for a real-time schedule management, but management also likes to know dates or a range of dates. So 10%, 90% confident limits were chosen, which is commonly used. It was easy to identify the 10 and 90% confidence limits since a statistical function had already been defined in Maple. The red line and the green lines show the confidence limits. The lines crossing the x-axis predicts a date for each of the confidence limits. To be even more concise, a table with confidence limits was generated to summarize the results. Since the confidence limit curves are already mathematically defined, it was easy to determine with Maple where the curves cross the x-axis. These numbers were translated into dates and entered into a table. All this was done automatically using Maple. So let's recap what we discussed. First of all, the FPGA was a very large semiconductor die with a large number of milestones. The schedule planning was very complex and would take a large amount of effort and time, so we needed an alternative method to control the schedule and predict key milestones that were needed. The method was to change from the normal time domain type analysis to a newer method that used the number of open major milestones as a function of time. Curve fitting techniques were used. The best curve was selected by reviewing the initial milestone value, the negative slope, the value of the square of rho squared, and did the curve cross the x-axis. Using stochastic analysis, both control limits and confidence information were calculated. The control limits were plus or minus 1, 2, and 3 sigma. When the new data point exceeded the plus or minus 2 sigma limit, an action plan was generated. If the new data point exceeded plus or minus 3 sigma, the action plan was executed. The action plan could either be some type of corrective or expedited action, or accepting the conditions that would continue and new curves would just be calculated. Finally, the 10 or 90% confidence limits were automatically calculated to provide specific dates. And again, these dates were automatically entered into a table. Special thanks. I wish to thank the following people and organizations that helped to make this presentation. I always like to give thanks to Dr. Lopez for all of his help. That includes all those webinars, Maple files that he sends me all the time and answering my many questions. Secondly, Johnny Gee, worked with him. We worked together many times at the local community college to generate solutions for all those classes that he teaches. And finally, to Maple Chip Technology for allowing me to use Maple and allowing the time for this presentation. So, any questions?
Thank you, Al. Can I just start? Please, anyone who has questions, please type it into the chat. Just to start, how large of a project would you say this could scale to? Like, so you gave the example, certainly a project near and dear to your heart. Would you imagine that this could then scale further with the development approach you took?
Yeah, so FPGAs are some of the largest semiconductors that are developed. This is what you were suggesting. So I've done program management for a lot of years, and I've done ASICs and et cetera, and some of those have been fairly large and complex, but this is by far orders of magnitude beyond a normal ASIC type stuff. So if you look at all the FPGAs that are out there, the number of IPs, normally in an ASIC design, you might have 5 or 10 IPs in it. This thing there's probably 20 or 30. Some of them are digital. Some of the IPs are mixed signal. There's massive amounts of memory and fabric inside. These are very large semiconductors. There might be some bigger, but not a whole lot bigger.
And you got to grips fairly well with the curve fitting commands in Maple, and it sounds like you had some support from other technology experts, I would say. Was that something that was a natural approach for you to consider sort of problem solving with Maple using the math modeling, or was this something you had been inspired to by seeing other applications?
Well, I've been using Maple for a while now, and I've always used mathematical stuff for all the jobs I've had over my career. And so I like Maple because it's flexible and it's a whole lot easier to use. This particular program, I kind of got stuck in that the scheduling methodology that they'd used was not working. It was they really didn't have a real program manager doing it, and it wasn't effective at all. But it was so massive and people were so busy that they didn't have time to do it correctly. And so what I ended up doing is trying to figure out how to come up with a totally alternative way of doing. So this technique never developed, and it was like, you got to do something, but nobody knew what. And so since there were a larger number of milestones, I kept looking and updating all the time, and I realized that there was information there. It was the time information was invalid, but there was information about were different IPs or different blocks done or not done. And I just thought, well, let me just track that and see if there's any kind of trend analysis. And there was. And it actually worked out fairly well, because what I showed is one chart, but there are actually 4 different areas. There's the digital IP design and there's the analog design. And so I had a chart for each one of those. And then for all of the designs, you have to verify it. So I had charts, there was milestones related to each of those. So there's actually 4 analyses going on in parallel. And 3 of them were very well behaved. But the 4th one, it required attention. And I was able to predict delays in the schedule before anybody else could see it. And I could predict when I thought it would come out. Sometimes there's periods, there's different design phases that you go, and some are a little bit harder than others. When you got those difficult ones, and all of a sudden you'd see it start to flatten out, and you could identify that there was going to be some delays. So not only could I predict that there was going to be a delay, but I could predict how long those new delays would be, when the new anticipated dates would be. And then everybody likes to have ranges of date, typical management type question, because this is not deterministic. When you do program management, the last thing somebody says, this is an exact date, it's silly, it doesn't exist. So I've always done in other stuff for Monte Carlo simulation, et cetera, for schedule. And I thought, well, let me put those ranges in this analysis. And that was good, because it gave people an idea of just how broad they could expect variance in the dates. So it was it kind of increased as we went along. What's nice about Maple is you start doing it and you realize, well, I can do a little bit more, I can do a little bit more. And all of a sudden it's a whole lot more than what you really anticipated at the beginning. So
thank you, Al. It does mirror a little bit of some things that are used in system engineering with planning for defense and aerospace. We have a question that came in. How do you mitigate changes within the process? Because I guess you would be able to determine which elements were the most risky or most in danger of missing.
Yeah, so the change control, when we got later into the program, change control was fairly minimal at the beginning. So I got into this program in the middle. It wasn't at the beginning. So most of the major change control stuff was done earlier. So I didn't have to worry too much about that. So my point was just whatever was happening was more of a pure schedule aspect versus trying to program management. I used to do program management, but I've always liked the scheduling part of it. So on this particular company, I'm really focused just on the scheduling part.
And just a follow-up question, would this have applications with design of experiments, DOA?
Yeah, I've done that years ago. I'd have to think about it. I mean, I don't think directly from when I've done it. It's been years since I've done that.
Well, thank you, Al. I really appreciate your time. Thank you also for answering the questions. That kind of brings this session to a close. I want to thank all of the speakers today and also the co-authors behind the scenes who worked to help them prepare and to publish the papers that these are based on. We hope you enjoyed the variety of topics that show just how applicable Maple is to both engineering sectors, research, and education. And certainly it demonstrates a lot of the skill and the talent of these speakers today.